Good morning everyone. We are group 3 and our roll numbers are 25 to 36. Today we are going to present our topic normalization in DBMS, but in little different and fun way. Instead of just explaining the theory, we created a small skit, a story style presentation. So sit back and enjoy.
Good morning, students. Good morning, sir. तो आज हम लोग कंटिन्यू करेंगे लिंक लिस्ट। लास्ट टाइम हम लोग ने लिंक लिस्ट स्टार्ट किया था, सिंगली लिंक लिस्ट हो गया था। आज हम लोग करेंगे डब्ल्यू लिंक लिस्ट। डब्ल्यू लिंक लिस्ट में 3 पार्ट होते हैं, डेटा और 2 पॉइंटर। एक होता है प्रीवियस पॉइंटर और एक होता है नेक्स्ट पॉइंटर।
सब वो तो हो गया पढ़ा।
डब्ल्यू लिंक लिस्ट पढ़ा के हो गया?
यस
अभी मैंने
लिखा है।
अरे ये तो मैथ्स की नोटबुक है।
नहीं सर,
कोई अपनी बुक दो।
सब मैंने लिखा हुआ है।
तूने लिखा है? लिखा। हाँ, डब्ल्यू लिंक लिस्ट तो पढ़ा के हो चुका है।
ये क्या हुआ बोलो।
यार नोट्स बनाए बट बहुत जमल हो गए, कुछ समझ नहीं रहा है।
तुम इतने अच्छे नोट्स कैसे बना रहे हो?
क्या हुआ, तुम लोग अभी तक गए नहीं?
सर इन दोनों में बहुत इशू है।
क्या है सर?
सर वो नोट्स बना रहे हैं हम बट वो मिक्स हो जाते हैं, कभी बाइफरकेशन समझते नहीं है। और इसके नोट्स देखो।
अच्छा तो मैं समझ रहा हूँ तुम लोग का इशू क्या है। रुको मैं तुम लोग को कहानी बताता हूँ। मैं तुम लोग को कहानी सुनाता हूँ एडवर्ड एफ कॉडी के बारे में।
Years, he was born in a modest town where the social rules were strict and very visible. From a young age, he noticed that people behave differently depending on who was watching, at home, at school, or in public. For example, he once observed that his neighbor, who was usually very playful, would suddenly act serious whenever an authority figure came by. These small observations stayed with him. Here, he realized that people often change their behavior not just because of rules, but because they want to be seen as normal, to fit in, to avoid judgment, or to be accepted. Puberty hit, life changed. He was working at IBM, and during that time, databases everywhere, not just at IBM, but across the world, were completely unorganized. Every department stored data in its own way. The same information, like customer's name or product details, was copied again and again in different files. If one file changed, the others didn't update, which led to confusion and mistakes. Data was duplicated, inconsistent, and difficult to manage. Now imagine EF Coddy sitting in his IBM office looking at piles of messy data printouts. He could see the problem right in front of him. Too much repetition, too much dependency, and no proper structure. That's when he started thinking deeply. There has to be a logical way to organize this, a way to make data cleaner, simpler, and more reliable. And right there in that office, surrounded by disorganized information, the foundation for what we now call normalization began to form.
Functional dependency. So when we learn about keys in database normalization process or various normal forms, we come across the term functional dependency. So in mathematics, you must have seen this. Simply means when A is given as an input to the function f, it computes and generates some output b. For example, let that function be a square function, which calculates a square of a number. And we provide an input phi to it. So simply by computing square of phi, which is 25, it will be computing as an output. Somewhat similar to this function is function dependency in database. For example, we have a table T having columns A and B. And if we write A goes to B, what does that mean? Like our mathematical example. It doesn't mean that if we have A, we can compute or generate B. It is different. It means that if we know the value of A, we can search or find or determine the value of B from a relation or a table. For example, if we are the given values of A as 2, can we find the value of B? So it checked the table and searched out 2 in column A. And corresponding to the 2, we get the value of B, which is DEF. So by using A, we got or found the value of B. So that means we can say that A determines B or B is determined by A. And we can say A determines B is a functional dependency. So in functional dependency, the attribute which is used to determine the other attribute is called determinant. And the attribute which is determined using the determinant is called as dependent. So, the definition of functional dependency states that a functional dependency is a constant that specifies the relationship of one attribute to another attribute in a relation or a table.
Now let us take an example for better understanding. Consider this relation or a table, and based on this relation, let us check whether the functional dependencies are valid or invalid. So for the first one, let us consider this functional dependency. Roll number determines student name, and department building. So as a roll number is considered as unique value for each student, definitely by using roll number, we can search or identify student name, and department building. For example, if we have roll number 3, we can uniquely determine the student name, and department building for roll number 3. So we can confirm that it is a valid functional dependency. So in a case where there are different determinants and corresponding different dependents, this kind of case is a valid functional dependency. Let us consider another case, using similar functional dependency as used previously. Department name determined department building. So department name EC determines department building B2, and department name ME also determines department building B2. Here, in this case, we have two different determinants, but the corresponding dependent values are the same. Is this a valid functional dependency? Yes, it is a valid functional dependency. There can be two departments present in a same building. Let us take another example. Another example can be roll number determining student name, where two students have different roll numbers but have same name. But still, it is a valid case. Therefore, this functional dependency is a valid one. So in this case, where there are different determinants and corresponding same dependents, it is a valid functional dependency case.
Functional dependency, student name determine department name. In the student name attribute, we have redundancy, two students have the same name. So if I asked you, tell me department name of student XYZ, you will find two different answers for it. One will be CS department and one will be from IT department. We cannot uniquely identify the department name just by using student name. Therefore, this functional dependency invalid one. So in a case where there are two same determinants and two different corresponding dependents, such a case is an invalid functional dependency case.
Types of functional dependency.
So let's start with the first type, trivial functional dependency. Consider A, this functional dependency A goes to B, or A determines B. If dependent B is subset of determinant A, then this dependency is trivial functional dependency. Let's take an example to clear the idea. Let us consider this employee table. From this table, we can write A functional dependency, employee ID and name. Determines name. Is it a valid functional dependency? Yes, it is a valid one. With the help of employee ID and name, we can determine the name attribute. It is definitely a valid one, but it is kind of useless. So the dependent attribute name is subset of determinant employee ID and name that is dependent is already present in the determinant. We are not getting anything new from it. Such kind of dependency is called trivial functional dependency. Now let us see the non-trivial functional dependency. It is just the opposite of trivial functional dependency. Again, let us consider a dependency A goes to B or A determines B. If dependent B is not a subset of determinant A, then only this dependency is said to be non-trivial functional dependency. Let us take the same employee table to get a clear idea. Consider the same employee table. Now, let us take another functional ID, functional dependency. Let us say employee ID and name. Determine age. We can determine age by using employee ID and name. So, it is a valid functional dependency. Now, if we observe the dependent age is not a subset of determinant employee ID and name, that it is dependent attribute is not present in the determinant. So, this kind of dependencies are non-trivial dependencies, where we finding something we don't already know, employee ID determines the name or employee ID determines age, are also some valid non-trivial functional dependencies.
What exactly is an action that dictionary definition that catches my attention is the third one to proposition that is assumed without proof. For the sake of study of consequences that follow from it, how the work is done by stating the consequences of some army stronger action are made to three distinct actions: reflexivity, augmentation, transitivity. What is reflexivity? Let's say that if A and B attribute in our relation and are also subset of attribute A, B, C, then we can also say that attribute A, B, C functionally determines attribute A and B. Augmentation, and let's say we have an attribute functionally determined B by augmentation, we can add one same attribute to both sides, and that would be still a valid function dependency. And the third axiom of Armstrong is transitivity. If attribute A function determines B and B function determines C, then function determines C. One aspect of Armstrong action is that they are sound. This means that if we have a set of function dependence F and we have function F closure, which is set of a function dependence that we call logically imply for F, and if we apply Armstrong action to F, we are not going to find any set of function dependency that go outside F closure. We only find things inside F closure. Another aspect of Armstrong action is that they are complete. This means that if you apply Armstrong action to F, we are going to find all the function dependency that exist.
From the three Armstrongs, action, reflexivity, argumentation, and transitivity, we can derive three rules called interference rule. The first one is named union rule, the second one is named pseudo-transitivity, and the third one is called the composition. Let's talk about the first rule, union interference rule. Here we have a pair of function independence determine B and A determines C. They have the same side. You can keep attribute A and union the attribute B, C. Now we have an attribute A that function determines B and C. The next interference rule is pseudo-transitivity. Let's say that an attribute of A function determines B and F closure and C determines F closure. In this case, all we have to do is replace B by, so we can derive to C as A determines D, and the last interference rule left is the composition, which works the opposite of the union interference rule. In this example, all we have to do is keep the left side and decompose the right side. An attribute of function A determines B and also determines C. Let's take a look at the schema R, where attribute A, B, C, D, and E and set of given function independence where A determines B, C, D and C determines E. B determines D and E determines A. I will start by using Armstrong first axiom, reflexivity. By reflexivity and attributes the term itself, we can watch comply. The A determines B
and B determines B, C determines C, D determines D, and E determines E. Using the inferential rule, the composition since A determines B, C, then logic imply that A determines B and A determines C. Now I will use the transitivity axiom to logic imply that since A determines B and B determines D, then A determines D. The union inferential rule let me launch imply that since A determines C and A determines D, then functionally the terminus CD. Using the transitivity axiom, our logic imply that because A determines CD and CD deter and A determines E, then A functionally determines E. Now I can use the union inferential rule to logic imply that since A determines A determines B, A determines C, A determines D, and A determines C, then A must functionally determine A, B, C, D, E. Again, the transitivity axiom allows me to logically imply that since A determines A and A determines A, B, C, D, E, then E also determines A, B, C, D, E. Once again, transitivity rule will allow me to logically imply that since CD determines E and CD also determines A, B, C, D, E. Now I will use the augmentation action. Just say that since B determines D, and if I add the same attributes to both sides of this function dependency, in the case attribute C, then I can derive to a valid function dependency where BC determines CD, and finally using transitivity axiom again logic that since BC determines CD and CD determines E, then BC functionally determines A, B, C, D, E.
In this video, let us discuss attribute closure. Consider a relation R with attributes A, B, and C. Let F is equal to A determines B and B determines C. By transitivity, we can infer A determines C. Also, we can infer A determines A by reflexivity. Using the union rule on all the three, we can infer A determines A, B, C. We can say that closure of attribute A written as A plus consists of A, B, C. That is, closure of A will contain all the attributes that are determined by A. Let us see what is the attribute closure of B. In F, we have B determines C. By reflexivity, we have B determines B. By combining both using the union rule, we get B determines BC. We cannot determine A using B. Thus, B plus or the closure of B includes only B and C. Let's now understand the definition of attribute closure. Given a set of attribute X and set of functional dependencies F, closure of X under F is the set of all the attributes functionally determined by X under F. Closure of attribute set X is denoted by X plus. Let us now consider a relation R with attributes A, B, C, D, and E. F is equal to A determines BD, BC determines DE, D determines E, and DE determines C. Let's find closure of A, that is A plus. A plus is initialized is equal to A. Now search for FDs having A as determinant. We have A determines BD. Add BD to the closure. Now A plus is equal to ABD. Check whether any FD has determinant as subset of ABD. D is subset of the closure. So using D determines E, we include E to the closure. That is, A plus is equal to ABDE. Similarly, using DE determines C, add C to the closure. Now A plus is equal to ABCDE. That means all the attributes in the relation R can be determined by A. Now let us compute the closure of attribute D. D plus is equal to D. Using D determines E, we can add E. Using DE determines C, we add C. Now other attributes can be determined further by D. Hence D plus is equal to DEC. Now let us find the closure of attribute set BC. BC plus is initialized to BC. Using BC determines DE, we add DE to the closure. Other FDs that can be considered are D determines E and DE determines C. But E and C are already included in the closure. Hence the closure of BC plus is equal to BCDE. Except A, all the other attributes can be determined by BC. We have seen that closure of A includes all the attributes. The remaining two closures do not include all the attributes. Hence A is the key for the relation R. Now let's discuss about this in detail in the next video. Using attribute closure, we can check whether an FD can be derived from a given FD set or not. To check whether an FD X determines Y can be derived from an FD set F, first compute X plus using F. If Y is a subset of X plus, then X determines Y is true, otherwise not true. Consider a relation R with attributes A, B, C, D, and E. F is equal to A determines B, A determines C, CD determines E, B determines D, and E determines A. Is CD determines AC logically implied by F? Compute the closure of set of attribute CD. CD plus is initialized by CD. Using CD determines E, add E to the closure. Now CD plus is equal to CDE. Using E determines A, add A to the closure. Now CD plus is equal to ACDE. Using A determines B, CD plus is equal to ABCDE. AC is a subset.
What is canonical cover and how to compute canonical cover for a set of functional dependencies using an example. A canonical cover or minimal cover, usually referred as FC, for a set of functional dependencies. F is a minimal set of functional dependencies that are further irreducible and are equivalent to F. Here equivalent means all the functional dependencies of F logically imply all the functional dependencies of FC and vice versa. Look at the example. Here F is the given set of functional dependencies and FC is its minimal cover. You can observe that the functional dependency A gives C of F is eliminated in FC as redundant functional dependency because C transitively dependent on A, and this can be inferred from FDs A gives B and B gives C. Minimal cover for a set of functional dependencies F can be computed using three simple steps. Step 1, insist on reducing the right-hand side of all functional dependencies into singleton attribute. This can be achieved using simple decomposition rule. Step 2, remove extraneous attributes if any. Extraneous attributes are simply redundant attributes which can be inferred from other attributes that are available in the left-hand side of same functional dependency. Step 3, we eliminate the functional dependencies that are redundant. We shall see more on each step with an example. In step 1, we decompose the functional dependency that has more than one attribute in its right-hand side. In order to have exactly one attribute, let us compute the minimal cover for the set F given here. Among the functional dependencies given here, only the functional dependency A gives BC has more than one attribute in its right-hand side. By applying decomposition rule, we can decompose this functional dependency into the FDs A determines B and A determines C. And we need to do this decomposition process for all the functional dependencies that have more than one attribute on their right hand side. Once completed, as a result of step 1, we arrived at the set of functional dependencies F1, which will further be used for computing minimal cover. This step is to remove redundant attributes from the left hand side of every functional dependency. To check whether an attribute alpha is redundant in a functional dependency, we compute the closure of left hand side attributes except alpha. If the closure includes alpha, then the attribute alpha is said to be redundant or extraneous in that functional dependency. To proceed, we brought forward the set F1. In this set of functional dependencies, we have only the functional dependency AB gives D has more than one attribute on its left hand side. In this functional dependency, there is a possibility that either A or B may be extraneous. To check whether A is extraneous in the functional dependency, we need to find the closure of the rest of the attribute, that is B here. So we find the closure of B, and the closure of B is equal to BC, which does not include the attribute A. Hence, we can conclude that A is not redundant. And also we need to check whether B is extraneous or not by finding the closure of A. And as a result, A closure include the attribute B. Hence, we can conclude that B is extraneous. As a result, we remove B from functional dependency AB determines D, and set F1 becomes F2 as shown here, and this will be taken forward for the step 3. Step 3 is to identify and remove any redundant functional dependencies. For instance, to check whether a functional dependency X determines Y is redundant in a set of functional dependencies F, we first exclude the functional dependency from F to form another set of functional dependencies F dash, that is F dash without the given functional dependency. Then we find the closure of left hand side attribute using only F prime. If suppose X, the closure includes the right hand side attribute, then we would say that the given functional dependency is redundant. Let us now check whether there are any redundant functional dependencies for our set F2, which we derived in step 2. We check whether the functional dependency A determines B is redundant or not. To do this, we have to first exclude the functional dependency from F2, then we get F2 the functional dependencies. A determines C, B determines C, A determines D. Now we find the closure of left hand side attribute, that is A, using only F2 dashes. So if I know A, I know C through this functional dependency. And if I know A, I know D through the functional dependency A determines D. Hence the result of A plus is equal to ACD, and this does not consist of the right hand side attribute B. Hence we can conclude that the functional dependency A determines B is not redundant. Hence we cannot exclude this from F2. Now let us take the second functional dependency A determines C and check whether A determines C is redundant or not. As usual, we exclude A determines C from F2, and we find the closure for left hand side attribute A, that is A plus, using F2 detail on. And as per F2 detail, if I know A, I know B. If I know B, I know C. So I know ABC as well as I know D. So A plus is equal to ABCD, which includes all the attributes from that relation as well as the right hand side attribute of A determines C is included here. Hence we can conclude that the functional dependency A determines C is redundant. Hence it can be excluded from the F2, and we can derive a new set of functional dependency F3 to proceed further. We remove the functional dependency A determines C as it was redundant, and we got a set of functional dependencies F3. Now let us check whether B determines C is redundant or not. We exclude B determines C from F3. We get F3 dash with only two functional dependencies. Now let us find the closure for left hand side attribute, that is B, using F3 dash, and there are no functional dependencies in F3 dash which has B on the left hand side. Hence, just by the reflexivity rule, B plus includes only B, so we can conclude that B gives C is not redundant. Let us move on to the next functional dependency, A gives D. To check whether A gives D is redundant, we exclude A gives D from F3, and we find the closure for A, which include A, B, C, not D. Hence, we can conclude that A determines D is not redundant as well. We have finished with all the functional dependencies of set F3. Also, we cannot further reduce F3 as because none of the functional dependencies of F3 is redundant. At this stage, we conclude that the minimal cover for given F is F3. F3 can be further written as A determines BD and B determines C. After applying union rule for functional dependencies, A gives B and A gives D. Now we can say that F logically implies F3 and F3 logically implies F. F3 and F3 logically implies F. That is, the functional dependencies of F can be inferred using FDs of F3 and vice versa.
Let us discuss about how to find candidate keys using attribute closure. An attribute or a set of attributes that uniquely determines all other attributes in a relation is known as a key. A set of attribute X in a relation R is a superkey of R if and only if the closure of X contains all attributes of R. In a table student with attributes roll number, register number, and name, roll number alone can uniquely identify all the other attributes. So roll number is a superkey. Register number also can uniquely identify all the other attributes. Hence, register number is also a superkey. Name cannot be treated as a superkey, as there is a possibility of having two students in the same class with same name. Any superset of superkey will always be a superkey. Hence, roll number, register number is a superkey. Roll number, name is a superkey. A candidate key is a subset of the attributes X in R with the following two properties. X plus includes all the attributes in R. That means candidate key is also a superkey. There is no proper subset Y of X such that Y plus includes all the attributes in R. That means a candidate key is a minimal superkey. In the example we have seen earlier, roll number is a candidate key. Register number is a candidate key. Roll number, register number taken together is not a candidate key because its subset roll number and register number taken alone is also a superkey. How to identify key using attribute closure? If the closure of set of attributes includes all the attributes in the table, then that will become a key in that table. Consider a relation R with attributes A, B, C. If is given as a determines B and B determines C, all attributes taken together is a superkey. That means A, B, C, D is a superkey. Whether A, B, C, D is a candidate key To check this, we have to find out whether any proper subset of A, B, C, D is a key. If any proper subset is a key, then A, B, C, D is not a candidate key. Let us now try individual attributes first. A closure is not equal to R, B closure is not equal to R, C closure is not equal to R, D closure is not equal to R. That means none of this serves as a key. We try combination of two attributes, A, B plus is not equal to RA, C plus is not equal to RA, D plus is equal to A, B, C, D. That means it includes all the attributes in R, hence AD is a super key. It is also a candidate key. Since no subset of A, B is a key, let us take another set of attributes, ABD plus is equal to R. That means ABD is also a super key, but it is not a candidate key. Since AD, which is a subset of ABD, is a super key, in order to find all candidate keys, try all subsets of R. This method is time consuming if the relation has more number of attributes. However, the candidate keys can be found more efficiently using another method. Categorize the attributes in the relation as required, not required, and optional. An attribute A is said to be a required attribute if A occurs only in the LHS of the FDS in F, or A is an attribute in a relation, but A does not occur in either LHS or RHS of any FDS in F. An attribute A is not required attribute if A occurs only in the RHS of FDS in F, and attribute A in relation R is an optional attribute if A is neither required nor not required. Consider a relation R with attributes A, B, C, D, E, F is given as a determines C, C determines B, D, and D determines A. Let us first categorize the attributes as required, optional, and not required. A appears on both sides, so it is optional. B appears only on the right hand side, so it is not required. C on both sides, so it is optional. D also optional. It does not appear on any of the FDS.
We know that a database table can have n numbers of records present. If this data is not well organized, or if it contains redundant data manipulation like insertion, deletion, updation on such tables can cause various anomalies or problems. Solution on these anomalies is the process called normalization. This normalization process is used to remove or minimize the redundancy from a table. Normalization process works through series of stages, which are called normal form. There are mainly 4 stages of normal forms: first normal form, second normal form, third normal form, and Boyce code normal form, or BCNF concept of first normal form. So without wasting any time, let us start after. So let's start. A table or a relation can either be in first normal form or cannot be in first normal form. For a table to be in first normal form, there are some conditions. Table must not contain composite attributes and must not contain multi-valued attributes. What is composite attribute? It is an attribute which can be further divided into parts. For example, name attribute. It can be divided into first name, middle name, and last name. Or another example can be address, which can be divided into street, landmark, city, state, pin code, etc. So if a table contains such composite attribute, it is not in first normal form. What is multi-valued attribute? It is an attribute which can have multiple values for single entity. For example, mobile number is a multi-valued attribute. An individual can have multiple mobile numbers, or another example can be of courses. An individual student can be registered to multiple courses. So if table contains such multi-valued attribute, it is not in first normal form. So if I show you this table and ask you whether it is in first normal form, your answer will be no. It is not in first normal form. It contains name attribute, which is a composite attribute, and it contains mobile number, which is a multi-valued attribute. So this table or relation is not in first normal form. But if we take a look at this table, it is the same table, but with some modifications. This table is in first normal form because we divided the composite attribute name into 3 simple attributes: first name, middle name, and last name. And the multi-valued attribute mobile number, we created 2 separate columns, mobile number and alternate mobile number. So this table does not contain composite and multi-valued attribute, and therefore this table is in first normal form. So if the table is not in first normal form, we can implement various methods to convert it into first normal form. Let's start with composite attribute. As we saw previously, name attribute is a composite attribute which are not allowed. So we divide it into first name, middle name, and last name. So the composite attribute is divided into simple attributes. Another example can be address. We can divide the composite attribute into house number, street name, city, and pin code.
From the relation or table. So as we studied previously, for a table to be in the first normal form, it has to satisfy some conditions. Similar to that, for a table to be in a second normal form, it has to satisfy some conditions as well. What are those? Let us see. First condition is that the table must be in first normal form, as it cannot be in second normal form if it is not in first normal form. Seems pretty logical. And the second condition is that the table must not have any partial dependency present in it. So if these two conditions are satisfied by a table or a relation, we can state that the table is in. First condition is table or relation must be in first normal form. There are 2 conditions for 1NF. No multi-valued attributes and no composite attributes. So if I show you this table and ask whether it is in first normal form or 1NF, what will be the answer? Answer is it is not in 1NF because this attribute mobile number is multi-valued. It has 2 values for each tuple, so it is not in 1NF. If we modify this table into this, then it can be in 1NF because each column is single valued. Let us take another example. Is this table in 1NF? Answer again is no. Courses attribute is multi-valued. Again, to solve it, we can make these following changes and then we can say it is in 1NF. See this following table. It does not have any multi-valued attribute. Is it in 1NF? Again, the answer is no. It does not contain multi-valued attribute, but it contains attribute name, a composite attribute which can be further divided. So again, this is not in 1NF. We can modify it like this to make it in 1NF. Consider this table and check if it is in 1NF. This also is not in 1NF. You must have guessed it until now. Yes, it contains composite attribute address. To make it into 1NF, we can modify it like this. So let us take one last example. This table is in 1NF as it has no composite and no multi-valued attributes present in it. So hope you understood the first condition for the table to be in second normal form. Second condition is there must not be any partial dependency. Let us understand this also with an example. Let us consider this table. To check whether there is a partial dependency in a table, first thing you need to identify is candidate key. In this table, just by using student ID, can we identify the complete tuple? No, there is redundancy present in it. Similarly, using course ID, we cannot identify complete tuple. It also has redundancies. Same is the condition with course fee. So if you look up closely, by using student ID and course ID, we can identify the complete tuple. That is, student ID and course ID closure will give us values of all attributes. So we can conclude that student ID and course ID together form a candidate key. There is only one candidate key in this table. Next step is to differentiate prime attributes and non-prime attributes. Prime attributes are attributes present in the candidate key. In our case, student ID and course ID. Remaining all attributes which are not part of candidate key or candidate keys are non-prime attributes. In this case, course fee is a non-prime attribute. So partial dependency definition states that if a non-prime attribute is determined by a part of candidate key, that functional dependency is a partial dependency. Let us check. Student ID and course ID determines course fee is one of the functional dependencies. In this case, complete candidate key determines non-prime attribute. Other than that, if you see, by using course ID, we can uniquely identify course fee. So this can also be a functional dependency. Now in this case, a non-prime attribute, course fee, is determined by part of candidate key, that is course ID. So this functional dependency over here is a partial dependency. And while this is present, table cannot be in the second normal form. So we found partial dependency in this table. To eliminate this partial dependency, we will split this one table into two. So what does eliminating partial dependency does? So this tries to reduce the redundant data from getting stored in the memory. Imagine there are thousands of students and records of those students are stored. Course fee is same for a particular course ID, but it will get stored thousands of times due to partial dependency. So this elimination of redundancy is the aim of second normal form. So if these two conditions are satisfied, then only we can say that the table is in second normal form. So this is all about second normal form. Hope you understood the concept very well.
Second normal form. Similarly, there are two conditions for third normal form. As well, first condition is that the table or relation must be in second normal form. And the second condition is that there must not be any transitive dependencies present in the relation or table. If any table satisfy these two conditions, then we can say that the table or relation is in third normal form. Let us understand both these conditions one by one. So the first condition is table or relation must be in second normal form. Let us take an example. Look at this following table. Let us identify if the table is in second normal form. It does not have any composite attributes. It also does not have any multi-valued attributes. Following are the functional dependencies for this relation. Based on these functional dependencies, we can conclude that there are no partial dependency present in this table. So these conditions means that the table is in first normal form, and it is in first normal form and has no partial dependencies present in it. These two conditions mean that the table is in second normal form. So this table satisfies the first condition for the table to be in third normal form. Second condition for third normal form is there must be not be any transitive dependencies present in it. Now, what is transitive dependencies? If A prime attribute A identifies non-prime attribute B and non-prime attribute B identifies non-prime attribute C, then A indirectly identifies C. These dependencies where A non-prime attribute determines another non-prime attribute is said to be transitive dependency. So let us understand with an example. This table is in second normal form. Now let us check if this table satisfies transitive dependency condition. In this table, employee ID is the prime attribute, and following are the functional dependencies for this table. First one is employee ID determines employee name and project ID, and the second one is project ID determines project name. So employee ID determines project ID and project ID determines project name. So indirectly, employee ID determines project name. Here in this transitive dependency, a non-prime attribute project ID determines another non-prime attribute project name. So in this table, transitive dependencies exists. So this table is not in third normal form. Now let us see how can we convert this table into third normal form by eliminating transitive dependency. To do so, we simply need to break down the table into different table. We will create a table project where project ID is primary key and project name is another column. In another table, we have employee ID which is primary key, employee name and project ID will be foreign key in this table. By doing this transitive dependency, project ID determines project name has been eliminated. So why exactly do we need third normal form? So we saw that even after table being in second normal form, the redundancy is still present in the table. We remove the partial dependency during second normal form, but still if there is transitive dependency, there will be redundancy present in the table. This is redundancy in larger database can take up huge space, but after converting the table into third normal form, redundancy has been eliminated from it.
If a table does not have any composite and multi-value attribute, then this two conditions mean that the table is in first normal form. A table that does not have partial dependency and it is in the first normal form, then these two conditions mean that the table is in second normal form. If a table does not have any transitive dependency and it is in the second normal form, then these two conditions mean that the table is in the third normal form. And finally, if a table is in third normal form and if left-hand side of every functional dependency of the table is a candidate key or a super key, then these two conditions mean that the table is in BCNF. So the two conditions for Boyce-Codd normal form are as follows. The first one is that the table must be in third normal form. The second condition is that every functional dependency in the table, say X determines Y, the left-hand side should always be candidate or a super key. If any table satisfies these two conditions, then we can conclude that the table is in BCNF. Let us try to understand these conditions using some examples. The first condition, we need to check if table is in third normal form. So let us consider this table as an example. In this table, no single attribute can identify complete tuple. So candidate key needs to be a combination. Using student and subject combined, we can determine teacher. So as student and subject combined, we can get complete tuple. It is a candidate key, and following are the functional dependencies for this table. Student and subject determines teacher, and using teacher, we can determine subject. If a table is in third normal form, then it is also in second normal form and also in first normal form. So we need to check right from first normal form. This table does not have composite and multi-valued attribute, so we can conclude that this table is in first normal form. For second normal form, we need to check partial dependency. In simple terms, there should not be any functional dependency. X determines Y, where Y is a non-prime attribute and X is a part of candidate key. If there is no functional dependency of this form, then the table is in second normal form. So let us check each FD of our table. First, student and subject determines teacher. Then this complete candidate key determines non-prime attribute. So this cannot be a partial dependency, as complete candidate key is used to determine a non-prime attribute. Let us check another FD. Teacher determines subject. In this FD, non-prime attributes determines part of candidate key. In this FD, there is a part of candidate key, but it is on the right-hand side. Partial dependency is when a part of candidate key is on the left-hand side. So this particular FD is also not a partial dependency. So this table does not have any partial dependency, and it is also in a first normal form. And therefore, we can conclude that this table is in second normal form. To check if a table is in third normal form, we must verify whether any transitive dependency exists. A functional dependency is transitive if a non-prime attribute determines another non-prime attribute. Let's analyze the given table. The first functional dependency states that student and subject determines teacher. Here the candidate key determines a non-prime attribute, so this dependency cannot be transitive. The second dependency states that the teacher determines subject. In this case, a non-prime attribute determines part of the candidate key, meaning a non-prime attribute determines a prime attribute. This does not satisfy the condition for transitive dependency either. Therefore, none of these functional dependencies in this table are transitive. Since the table is already in second normal form and has no transitive dependency, we can conclude that the table is in third normal form. We have proved that this table is in third normal form. Now to check if it satisfies Boyce-Codd normal form, we need to verify that every functional dependency in this table is in form of X determines Y, where the left-hand side X is a candidate key or a super key. Let's examine these dependencies. The first functional dependency states that student and subject together determines teacher. Here the left-hand side is a candidate key, so there's no issue. The second dependency states that teacher determines subject. In this case, a non-prime attribute determines a prime attribute. Although this dependency is neither partial nor transitive, the left-hand side is not a candidate key or super key. Hence, this FD violates the BCNF condition. To transform the table into BCNF, we need to decompose it. The original relation R, where student, subject, teacher, will be split into two tables. R2 will have teacher and subject as attributes, where teacher is the primary key. R1 will have student and teacher, where student is the primary key and teacher acts as a foreign key, referencing R2. After decomposition, the relation is successfully transformed into Boyce-Codd normal form.
And this is normalization in its entirety, just like EF Coddy thought of.
तो ये थी कहानी नॉर्मलाइजेशन